Hello everyone, we're Chemical Engineering Group number 18. My name is Blaze, and along with Nick and Noor, we are one of the two groups who had the privilege of working with Dr. Sun this semester on our project, Sustainable Plastic for a More Sustainable World. While the other group worked on upstream solution to the crisis, our group focused on possible solutions from a downstream approach. While upstream innovation is addressing the problem at the design stage, a downstream approach to a problem is the intervention of it after they already exist. A couple example includes the method of disposal, degradation, recycle, and remediation of plastic materials. From depletion of non-renewable resources to greenhouse gas emissions, if the plastic crisis remains unaddressed, it can lead to major repercussions in the future. However, it is hard to abandon plastic entirely due to the influence it has on our social and economic development. Mechanical recycling is limited by cost and the quality of products, while natural biological decomposition can take up to many years and adds another step in the sorting process. Chemical recycling is the best option out of the three because it breaks it down to molecular level and is a faster process than its counterparts. Along with recycling, it is helpful to repurpose old plastics into functional items. However, some plastics are non-recyclable or repurposable, which brings us to the topic of microplastics.
Microplastics are particles of plastic that are smaller than 5 millimeters in diameter. Due to their small size, they pose many potential dangers to animals and the environment. Microplastics have a hydrophobic nature, which makes them easily transported through waterways via wastewater runoff. These microplastics can be ingested by marine animals and are absorbed into their invertebrates, causing pathological stress, reproductive impediments, interference with enzyme activity, and stunted growth. One possible solution to cleaning up these microplastics is microbial degradation. Microbial degradation allows easy control in plastic pollution as the plastic fragments are used as a carbon source for growth of microbes. Microbial degradation has several reactions that can be used, including biodeterioration, biofragmentation, biosynthesis, and mineralization.
Promising solutions for downstream issues are new bioplastics like PLA, PHA, and PCl. New polymers are easier to dispose of and reuse and don't last as long in nature as petroleum-based plastics in the event of improper disposal.
For our experimental phase, our objective was to test thin PVA, MMT, nanocomposite coatings capability as an alternate to plastic in packaging and storing products, which were fabricated by a one-step co-assembly process and then investigated for the effect of a polymer's degree of hydrolysis on the performance of the coated substrate through a flow-induced orientation technique. In order to optimize the PVA, we studied the effect of different molecular weights, degree of hydrolysis, and the addition of a cross-linking agent, glutaraldehyde, on the oxygen and water vapor barrier properties under two conditions, one standard and one extreme.
The optical clarity of the coated films was quantified by recording the visible light transmitted. Coatings with PVA are nearly as transparent as PLA regardless of molecular weight. A slight reduction in optical quality can be observed with PVA 15 to 99. This reduction of optical quality continues as montmorillonite is added in a 50-50 ratio with the PVA binder. The interlayer distances in X-ray diffusion results also suggest that montmorillonite undergoes co-assembly to align to one another while being subjected to shearing stress during the coating process. Oxygen permeability and water vapor permeability were also studied.
We can conclude that the oxygen transmission and water vapor transmission data reveals that high degrees of hydrolysis improves the barrier properties of the nano coatings, so with an increase in degrees of hydrolysis of PVA, the oxygen transmission and water vapor transmission of coated PLA decrease. The cross-linking processes of the glutaraldehyde improve these barrier properties as well, and in general, higher degrees of hydrolysis binder materials are desired for strengthening the PVA coating against vapor transmission. Different disposal methods have different effects on the plastics. Upcycling can create more valuable products from discarded plastics. Recycling can decrease physical properties in the case of mechanical recycling and breaks plastics down to the molecular level so it can be useful for many applications in the case of chemical recycling. Through composting or downcycling, plastics can be broken down into separate components for remanufacturing of new plastics. Bioplastics offer a potential solution to the plastic crisis, and use must increase in the coming years. As technology develops and advances, better production and disposal methods can lower costs of these new materials and one day lead to a closed-loop cycle in the plastic industry.
We'd like to thank our mentor, Dr. Sun, and Dr. LaChance, and Maria Faruqi, and also the upstream group members for assisting us in finalizing our project. Thank you for watching.